I'm going to take a short detour and talk some more about the all-pass filter block. I've demonstrated that it produces phase shift, rotating the signal about the time axis. But that's not the whole story. I'll start with the all-pass filter tuned to its minimum frequency. At this tuning, it has no effect on the 1 kHz wavelet. Next, I'll apply a time window to the wavelet. This tapers the beginning and end. And next, I'll outline the envelope of the wavelet signal. I'll now advance the tuning of the all-pass filter to the frequency range of the wavelet. Two things happened. The phase advanced, and the signal envelope was delayed. In the signal processing world, this is called envelope delay, or group delay. Group delay is another way of presenting the phase shift caused by the all-pass filter. At 1 kHz, the all-pass filter produces about 1 millisecond of group delay and 180 degrees of phase shift. It differs from signal delay in that 1. It's frequency dependent, 2. It changes the shape of the signal that passes through it, and 3. It can be realized with passive components, whereas a practical signal delay requires active circuitry. A signal delay can align two signals with respect to time, but an all-pass filter is required to align them with respect to phase. We may need some of each when aligning the sub with the main. Here are the components that need to be considered with regard to alignment. I'll start with someone's full-range box. It can be active or passive, but it's crossed over and aligned internally. That's most often the case with modern loudspeakers. I'm going to augment that with a subwoofer, a passive unit with an appropriate external amplifier. This necessitates a crossover block in the DSP. I've chosen a crossover frequency of 125 Hz, and I've done my homework to make sure that the full-range box extends that low and the subwoofer extends that high. Part of the system design process is to make sure that you have components that can work well together. Let's put the signal processing on hold for a few minutes and talk about loudspeaker placements. Alignment is most meaningful when the full range and subwoofer systems are together, either ground stacked or flown. This assures the same path length difference between the two over most of the audience area. If you place the sub under the stage, you can still align at a reference point, but it won't hold up over a large area. Either way, the alignment process is the same. My setup in REW is important. Here's what I've done. I've opened the signal generator and oscilloscope. The generator is set at the crossover frequency between the sub and full range box, 125 Hz in this example. I'm using a wavelet of 6.5 cycles with a hand window, and I've set the repetition rate to be slightly longer than the room's decay. Channel 2 on the audio interface remains looped back to the Channel 2 input, and I've checked the box to send the signal to the timing reference output. This assures that the wavelet is playing to both output channels. One feeds the system, the other is the timing reference. Earlier, I used this setup to measure the DSP. This time, I'll repatch to measure the system's acoustic response at a microphone. The scope is set to trigger on Channel 2, the timing reference. And here's the measured timing signal. I'll place a cursor to mark its start point. That leaves a second cursor to line up on the measured signal. The time axis is scaled to 20 milliseconds per division, letting me see a time span of about 200 milliseconds. That's more than enough for even a large room. Using this setup, I've turned a 2-channel oscilloscope into a single-channel scope with an absolute time reference. I can use it to measure the arrival time and shape of the wavelet at a measurement position. We're ready to go to work. Here are my processing blocks in the DSP. To keep things simple, I've used the same processing blocks for the full range and the sub. There are other possibilities. I'll begin by opening the crossover block in the DSP and muting the sub. We'll consider the systems independently for alignment. Step 1 of the alignment process is to check the polarity of the sources. This is extremely important. The two components you're trying to align ideally should be polarized the same. This step can be done in the shop, in the parking lot, or in situ. Our oscilloscope test setup makes a good polarity tester, so I'll use it. It helps to have some free space around the mic and loudspeaker. This can mean a tall mic stand for the mains and a ground plane measurement for the sub. This is a reason why it's good to check polarity before the installation. To save time, let's assume I've done that on the sub. I'll show how to use wavelets to check the full range box. With the sub muted, I'll catch the full range box. Since the crossover filter is in place and the wavelet frequency is 125 Hz, the phase shift of the crossover filter may make the polarity indeterminate. One way to handle this is to select a higher frequency wavelet. I'll go up to 400 Hz, well away from the crossover frequency. Note that the reference signal and measured signal look identical. The center peak is positive, and the wavelet is symmetrical about it. But while we're here, let's make another observation. By measuring in the time domain, the wavelet is anechoic. The room reflections always arrive after the wavelet. With a long repetition rate on the signal, we're not competing with reflections, reverberation, or room modes, only the room's noise floor. You have to compete with all of these in the frequency domain using the real-time transfer function. Now that I know the polarity is correct, I'll return to 125 Hz and scale the vertical axis. Now the wavelet is not symmetrical, meaning that there is some phase shift caused by the crossover. I'll open the all-pass filter and apply a slight amount of phase shift, just enough to make the wavelet symmetrical. You can add phase shift with the all-pass filter, but you can't remove it. I'm adding just enough to achieve symmetry. The wider appearance of the measured signal is due to the group delay of the crossover filter. The envelope of the waveform has been delayed. This gives it the bloated appearance due to the added cycles. I'll close the all-pass filter and return the vertical axis to the original setting. This is the full range box, properly polarized and phase shifted to appear symmetrical. It's the target response for the subwoofer, which I'll do next.